Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
The 1931 publication of Karl Menger's Dimensionstheorie represents the pivotal moment of synthesis and crystallization in the development of model topology, arriving amidst a fertile period of foundational inquiry. A monograph sought to establish a comprehensive, rigorous, and broadly applicable theory for one of mathematics' most intuitive yet elusive concepts, dimension. This essay undertakes a direct and systematic evaluation of the central claims, theoretical frameworks, and internal logic presented within the principal sections of Menger's work. The analysis will proceed sequentially through the book's core arguments, from its foundational definitions to its profound theorems on embedding and universal spaces. The objective is to assess the work on its own terms, examining the cogency of its proofs, the utility of its constructs, and the successful fulfillment of its ambitious goal to transform the idea of dimension from a vague geometric intuition into a powerful and precise analytical tool. We will explore the mechanisms by which Menger built his edifice, evaluating the strength of each intellectual beam and the soundness of the overall structure he bequeathed to 20th century mathematics. Section 1. The inductive definition and the pursuit of generality. Menger's work commences by confronting the primary challenge of its subject, the formulation of a definition of dimension that is both mathematically rigorous and applicable beyond the familiar confines of Euclidean spaces. The central claim of the book's opening sections is that an inductive, or recursive, definition provides the most powerful and coherent framework. Menger posits that the dimension of a space can be defined relative to the dimensions of certain of its subsets. The book's foundational argument begins with the concept of a zero-dimensional space. Menger claims that a metric space possesses dimension 0 for every point within the space, and for any positive distance epsilon, there exists an open neighborhood of that point, with a diameter smaller than epsilon, whose boundary is the empty set. This establishes a baseline of perfect disconnectedness. From this starting point, the inductive claim unfolds. A space is said to have a dimension less than or equal to the positive integer n if, for every point and every positive epsilon, there exists an open neighborhood of that point, smaller than epsilon, whose boundary is a set with dimension less than or equal to n-1. The dimension of the space is then the smallest integer n for which this condition holds. The evaluation of this claim reveals its profound efficacy. The methodology is one of elegant recursive logic, building complexity from a simple, verifiable base case. The evidence for its power lies in its immediate applicability to general separable metric spaces, a domain far wider than that of classical geometry. Menger's framework successfully captures the intuitive notion that a line, a one-dimensional object, is separated by points, which are zero-dimensional objects. Likewise, a plane, which is two-dimensional, is separated by curves, which are one-dimensional. The genius of the internal claim is its abstraction of this principle. The argument detaches the concept of dimension from visual representation and re-establishes it as a purely topological property concerning the structure of boundaries within neighborhoods. This formulation, developed in parallel with the work of Pavel-Arison, demonstrates its robustness by yielding expected results for simple spaces while providing a clear method for classifying more complex, pathological constructs. The claim of the book's first part is thus validated by its logical coherence and its expansive utility, providing a stable axiomatic footing for the entire theoretical structure that follows. Section 2. Dimensional invariance and the sum and product theorems. Having established a working definition, Menger proceeds to demonstrate that his concept of dimension behaves as a reliable mathematical invariant under common set theoretic and topological operations. The central claims of this portion of dimensions theory are embodied in a series of powerful theorems most notably the sum theorem and the product theorem. The sum theorem for closed sets asserts that if a separable metric space can be expressed as a countable union of closed subsets, where each subset has a dimension less than or equal to n, then the entire space also has a dimension less than or equal to n. This is a claim about the stability of dimension under countable aggregation. The evaluation of this theorem reveals its critical importance for making dimension a workable property. The proof Menger presents is a meticulous construction, demonstrating that any attempt to find a boundary of dimension n within the larger space can be localized to one of the constituent subspaces, leading to a logical contradiction. The claim is sound and its implication is that dimension is a maximal property. It is determined by the most complex parts of a space, a finding that aligns with geometric intuition. The second major claim concerns the behavior of dimension with respect to Cartesian products. The product theorem addresses the dimension of a space formed by the product of two spaces, say x and y. Menger's argument establishes the inequality that the dimension of the product space x cross y is less than or equal to the sum of the dimension of x and the dimension of y. The proof of this theorem is considerably more intricate, involving a delicate analysis of how neighborhoods in the product space are constructed from neighborhoods in the factor spaces. The claim's significance is immense, as it provides a predictable, albeit bounded, rule for calculating the dimension of higher dimensional spaces built from lower dimensional ones. For example, it confirms that the product of two one-dimensional lines yields a space of dimension at most 2. The internal methodology relies on a sophisticated induction on the sum of the dimensions, while this inequality was the focus. The question of when equality holds became a major research program, highlighting the depth of Menger's initial formulation. The evaluation of these theorems confirms their claims. They equip the theory of dimension with an arithmetic, transforming it from a mere classificatory scheme into a dynamic analytical calculus. Section 3. The universal curve and the essence of one-dimensionality. Menger next applies his theoretical machinery to a specific and foundational case, the nature of a curve. The section's primary claim is a bold redefinition. A curve is any one-dimensional continuum. A continuum is a compact and connected metric space. This definition is a purely topological one, dispensing with any classical requirements of smoothness or differentiability. The evaluation of this claim is an assessment of its power to unify a vast collection of objects under a single, rigorous concept. Menger's work here demonstrates that this abstract definition encompasses everything from a simple line segment to a space-filling curve, provided the latter is properly understood. The internal argument is that the property of being line-like is fundamentally a matter of having dimension 1 to substantiate this claim. Menger introduces one of his most celebrated constructs, the universal curve, now widely known as the Menger sponge. The book makes the extraordinary claim that this specific, constructible object is a universal one-dimensional space. The universality claim means that any one-dimensional separable metric space is homeomorphic to a subset of the Menger sponge. This is a staggering assertion of completeness. The methodology for its construction is an iterative geometric process. One begins with a solid cube. In the first step, the cube is divided into 27 smaller, congruent cubes, and the central cube along with the 6 cubes in the center of each face are removed. This process is then repeated infinitely on each of the remaining 20 smaller cubes. The object that remains in the limit is the Menger sponge. Menger's analysis claims, and rigorously proves, 2 key properties. First, the resulting object is a one-dimensional continuum according to his definition. Second, it possesses the asserted universality. The evaluation confirms the soundness of these claims. The proof of universality is a masterpiece of constructive topology, showing how any curve can be progressively mapped into the sponge's intricate structure. The Menger sponge stands as a powerful piece of evidence for the entire theory, a tangible paradox. It is both a simple geometric iteration and an object of infinite topological complexity. perfectly illustrating the abstract power of the one-dimensional definition. Section 4, the embedding theorem, and the link to Euclidean geometry, a purely abstract theory of dimension risks becoming a self-contained logical game. Detached from the geometric world it aims to describe, the penultimate major section of dimension theory confronts this risk head-on with a profound claim about the relationship between abstract dimension and concrete geometric space. This is the Menger-Nöbeling embedding theorem. The theorem's central assertion is that any n-dimensional compact separable metric space can be topologically embedded as a subset of a Euclidean space of dimension 2 times n plus 1. An embedding is a homeomorphism onto a subspace, meaning it preserves all the topological properties of the original space. This is a claim of geometric realization. The abstract, intrinsic property of dimension places a specific, quantitative limit on the complexity of the ambient space required to convey. The evaluation of this claim uncovers one of the deepest and most impactful results of the entire work. The methodology of the proof is highly sophisticated, requiring the construction of a mapping from the abstract space into the higher dimensional Euclidean space and then showing that this mapping is a one-tune, continuous function with a continuous inverse. It involves concepts of general position, ensuring that points are mapped in a way that avoids self-intersections or other dimensional degeneracies. The power of this theorem is twofold. First, it provides a powerful validation of the dimension definition itself. The abstract number n derived from the inductive definition is shown to have a direct, physical-world consequence. It determines how much room a space needs to exist without crushing its own topological structure. Second, the theorem provides a bridge, allowing the powerful tools of analysis and geometry within Euclidean space to be applied to the study of abstract n-dimensional spaces. The intellectual elegance here is palpable. Menger demonstrates that a space is n-dimensional if and only if it can be deformed into a subset of the space R to the power of 2n plus 1 where every point, as arbitrarily small neighborhoods whose boundaries with a set of dimension at most 0. This provides an alternative, equivalent definition of dimension. Tying the theory together, the claim of the embedding theorem is thus one of the book's crowning achievements, cementing the relevance of the abstract theory to concrete geometric inquiry. Section 5, Synthesis, and the invariance of domain. Throughout the book, Menger's overarching project is one of synthesis, aiming to create a single, unified theory from the brilliant but sometimes disconnected insights of his predecessors. A key implicit claim is that his framework provides the definitive context for understanding one of topology's most fundamental results, Brouwer's theorem on the invariance of domain. Brouwer's theorem states that for any open subset U of an n-dimensional Euclidean space and any continuous, on-tune mapping f from U into that same space, the image f of U is also an open set. A direct consequence is that two Euclidean spaces, one of dimension m and one of dimension n, can be homeomorphic only if m equals n. This is the very foundation of what we mean by dimension in geometry. Menger's dimension theory claims to provide the most natural and powerful language for proving and understanding this invariance. The evaluation of this claim shows how Menger's work provides the final, essential piece of the puzzle. While Brouwer's original proof was a landmark, Menger's theory of dimension offers a more profound explanation for why it must be true. The internal argument of Menger's book demonstrates that dimension, as he has inductively defined it, is a topological invariant. This means that any two spaces that are homeomorphic must have the same dimension, because Menger's definition correctly assigns the dimension n to n-dimensional Euclidean space. The invariance of dimension follows as a direct and elegant corollary of his general theory. The proof is no longer an isolated, albeit brilliant, result about Euclidean space. It becomes a special case of a universal principle governing all separable metric spaces. Menger's framework, therefore, fulfills its claim of synthesis. It absorbs Brouwer's deep result, places it within a more general and powerful conceptual system, and in doing so, solidifies the very concept of dimension as the fundamental topological invariant that distinguishes one Euclidean space from another. The work provides a satisfying and complete explanation for a principle that had been a central, motivating question for the entire field. In conclusion, a direct evaluation of the claims within Karl Menger's 1931 dimension theory confirms its status as a masterwork of mathematical exposition and theoretical consolidation. The book succeeds unequivocally in its stated and implicit goals. Its inductive definition of dimension proves to be a robust, general, and logically sound foundation. The core theorems on sums and products provide the necessary algebraic machinery to make the theory a practical and powerful tool for analysis. The rigorous definition of a curve and the construction of the universal sponge offer a compelling and concrete demonstration of the theory's power to handle both intuitive and pathological cases with equal aplomb. Furthermore, the Menger-Nöbling embedding theorem brilliantly fulfills its promise of connecting the abstract, topological notion of dimension to the concrete world of Euclidean geometry. By reframing and subsuming foundational results like the invariance of domain, the work provided a definitive, unified language for an entire branch of mathematics. Menger's monograph is more than a summary of results. It is a coherent and compelling argument, presented with methodical clarity, that dimension is a fundamental, calculable, and deeply meaningful property of abstract spaces. Its enduring significance rests upon the strength of these internal claims, each one a carefully forged link in a chain of reasoning that elevated dimension theory to a major and essential pillar of modern topology.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.